You're watching the MotionWorks IEC hardware configuration video tutorial series. This section teaches how to configure the most basic settings of each servo axis. Hi, I'm Matt Pelletier. Here's a quick preview of what we'll do. Now that you're familiar with the hardware configuration, let's fully configure the demo hardware for an application. We'll optimize the MECHATROLINK-III settings, figure out the mechanical units, and set some basic servo parameters like over travel, direction, incremental encoder, and single-phase power. The axis data copy-paste feature will help us speed things along, and I'll give you the challenge of setting up a rotary table axis on your own. To follow along in this tutorial, you'll need connection to one of our MP3300 IEC and Sigma 7 demo units. If you would like remote access to one of these demos, please request by email to training@yaskawa.com. You can see how this works in the remote connection e-learning video. And you can see here I have connection to the demo through the web UI and the remote I/O. First, let's start with all the demo hardware at default conditions. We have a couple of videos that show how to reset to factory default, but rather than go through that process, I've prepared a project at factory default for this demo. Then all we need to do is delete the project archive and we can go online. From MotionWorks IEC, and I'm running version 3.3. Please go to File Open, navigate to that Class Materials download, and open the hardware config project. Let's unzip it. I recommend you open the ZWT project and unzip it again, just to be sure you have the original. I'm going to unzip it to the projects folder, so click No, and navigate to C, Users, Public Documents, MotionWorks IEC3 Pro, Projects, and save. This will overwrite the one that you may have worked with in the previous video. So yes, and yes. You can overwrite your libraries, yes to all. And now, just for organizational purposes, let's rename it File Save As Basic Axis Configuration, shortened up name there. And let's look at the hardware configuration. And before you go online, let's first delete any project that you or a previous user might have been running on the controller. Go to the web UI and log in. And remember, under Setup, go to Archive and hit Delete and reboot. Now back in hardware configuration, you can set your IP address for your controller. And I can see the controller's finished rebooting. So I'll go ahead and hit connect. Do we choose what's on the controller or what's in the project? We would choose what's in the project since that's the configuration that we're trying to use. The default configuration, choose offline. Now the first part about setting up the axes has to do with the MECHATROLINK-III network over which all of the axes are connected. So would you please click on that in the hardware tree? And let's see what we have here in detail. You see we have the three different axes here listed in the table. There's a communication cycle and cycle usage graph. The communication cycle determines how fast the controller communicates with the servos over the network. And it's set to 4 milliseconds by default. It's the slowest. And this graph on the right shows the 4,000 microseconds, 4 milliseconds, and how much of that cycle is being used by MECHATROLINK communication. Let's change the cycle to 1 millisecond. And I think now it becomes more clear that there's about 160 microseconds used. Part of that is the response time of each network node, meaning each of these three servos, all added up here, these response times. Another component is the retries. A third major component is the hot plugging, which means if a device is powered off, it will be able to come back online with the controller as soon as it powers back up. And there's a little sliver of time due to overhead. And the remaining 840 microseconds or so is available then to run your code. That is, the programs running in the different tasks, fast, medium, and slow in this project. So it comes down to balancing having fast code and having fast MECHATROLINK network in order to optimize the performance of your machine. You might think that a faster communication cycle is always better, but the faster you set the MECHATROLINK communication cycle, the less time is left for the code. For example, choose 0.5 milliseconds, and you can see that there's relatively speaking a lot less time left to execute your code compared to how much time is dedicated to communicating to the servos. Also, if you look under the Advanced tab here, there is a maximum number of nodes, in this case meaning the servo axes, maximum number that can even theoretically exist for the communication cycle that you've selected. As your application development proceeds, it will be important to balance the communication cycle with the scan times of the tasks running your programs. A low cycle time may be great for high performance applications with minimal programming, but a higher cycle time will be necessary as the number of servos increases and the code complexity increases. Let's start off with 1 millisecond, since there are only 3 axes in the system, and I don't expect the code to get too complex for this demo. Now, what about max retries? Max retries is a distinguishing feature of MECHATROLINK as a network protocol, and it basically means that there is communication time reserved to send a data packet that may have been corrupted by electrical noise. So the higher you set the retries, the more robust the network communication becomes. For example, choose 4, but you can see that the retries contribute significantly to the communication cycle, which in turn takes away time to execute your code. So again, you need to balance the max retries with the scan times of your application program tasks. I don't expect a lot of electrical noise in this demo, so I think I'll just put the retries back down to the default of 1. Now, finally, there's these settings here for default response time and change response times. The response time is just how much time the communication to the device actually takes. And it depends on the network topology and the length of the cables. This table below shows both configured and measured response time, which you want to match. And if they don't match, then you can use change response times and choose to measured response times. Now, if you were to add an axis that's not yet connected, I'll do that here just as an example. Right-click Add Device, and add another SGD7S as node 6. Of course, it can't read it. That's why you get this error. And so, of course, the response time for this axis cannot be measured since it's not really there. And so it uses the default response time temporarily. Once the axis is online, then you'd want to come back in here to hardware configuration and choose measured response times again. Of course, we don't really have this on the demo, so I'm going to right-click on it in the table here and click Remove Device. Okay, our MECHATROLINK network is set up. Might be a good time to save. And for the sake of time, we won't power cycle yet. We'll do one power cycle after we've set up all of the axes here. On this demo, let's call the 2 motors on the left axis X and axis Y and set them up as timing belt actuators. If this timing belt actuator has a drive pulley with 5 millimeters between each tooth and 72 teeth, then this will result in 360 millimeters per motor rotation, and that will line up nicely with the markings on the wheel. These servo motors are driven by the dual axis SGD7W, which is wired for 200 volt power single phase. Okay, so both of these axes are the same. The third axis we'll call axis Z, and let's model it as a rotary table with 360 degrees per rotation. This is simply a motor directly coupled to the wheel. And you can tell it's driven by the SGD7S, the single axis amplifier, and it runs on 100 volt single phase power. Please follow along with me and let's set up the x-axis together. This is axis 3 in the MECHATROLINK tree. So click on that. Under the configuration tab, the axis name here is in the table toward the bottom. We can change that from axis 3 to capital X. It's reflected now in the tree. Right above that is an important parameter called load type. This refers to the movement of the mechanism, in this case linear, and it also implies finite move distance. The machine cycle at the very top of the page applies only for axes with infinite movement, in which case you would set the load type to rotary. When we set to linear, finite, then the machine cycle is ignored. You can just leave it set to 1. The feed constant is the number of units the mechanism moves per rotation of the load shaft, the drive shaft into the mechanism, and not including any gear reduction. Common user units are available in the pull down at the right here, and it's just for reference. This setting does not at all affect the operation of the controller. In this case, we said that the drive pulley resulted in 360 millimeters per rotation. So we'll put in 360. If we had a gearbox, the gear ratio is the number of rotations out over the number of rotations in for all of the combined transmission components. So a 5-to-1 gearbox would be 1 rev out and 5 revs in. We don't have any gearing in this example, so just leave that at 1-to-1. That's about it for basic settings on this tab. So let's skip past the limits tab to overtravel. Overtravels are inputs to the servo amplifier that by default must be connected in order to allow the motor to move forward or reverse. This way the amplifier can use proximity sensors to detect the load and stop the mechanism from moving too far. Our demo doesn't have any I/O connected to the amplifier, and in fact if you look with the camera, you can tilt down here and you can see there's not even a connector plugged into this amplifier. So let's set the overtravel parameters to a setting of 8. Set the signal to always enable forward. And the other one for negative, same thing. Number 8, set the signal to always enable reverse. We're basically disabling the overtravel feature for this axis. And there are a number of options available if you were to use overtravel, which we will touch on in the next video. For now, let's skip ahead to the function tab for a few more of the most important parameters. And this top one here, rotation direction, is really one of the most basic, meaning which direction on the motor is forward on the machine. You have either counterclockwise or clockwise. Let's leave it at counterclockwise because this way, if you look at the demo, let me tilt back up, a counterclockwise motion on this motor will result in an increasing value printed on the indicator. In the function tab, still further down, also is the power selection. You may recall that this amplifier is wired for 200 volts single phase. However, this amplifier can also be wired for 200 volt 3-phase, which is the default. So let's choose apply single phase power. And this is the reason why you may have an alarm on this axis already. And the alarm is probably AF10 power line open phase. It does depend on what the current configuration is in the amplifier, whether you see that alarm or not. That's why I don't have it. But once we save this and reboot everything, that alarm will go away. Let's move over next to the Absolute Encoder tab. We've already worked with the Absolute Encoder faults in some of the previous videos, And later in this training course, we'll investigate absolute encoders in detail. But for now, just for simplicity, let's set the absolute encoder to function as an incremental encoder, setting number 1. And these are the most basic configuration settings to consider when you're just trying to get an axis up and running. So let's save again before moving on. And again, let's hold off on the reboot until we get all the axes configured. So click OK here. And there's a real nice feature now in the hardware configuration where if you have axes requiring very close to the same configuration and the same drives and motors, you can save a lot of time by copying from one axis to the other. And I think since we're modeling both of these as timing belt actuators, this is a good chance to use that feature. And all you do is right-click in the tree, choose Copy Parameters, and then right-click on the axis you want to copy them to, paste the parameters. For some reason on this remote connection, it seems to take quite a long time to paste this. It's a lot quicker when you're directly connected. And if you had many axes, you could even right-click Paste to multiple axes and choose the axes you want to paste to. And pasting will not be possible if the hardware is not a close match. That's why axis 5 is not available here. And you probably noticed that the axis name was not copied. Every axis has to have a distinct name. So let's change axis 4 here to Y. And one more difference on this axis is the direction. If you visualize it here, maybe you can tell that this motor will have to turn clockwise in order for the printed numbers to increase. So go ahead and change the direction parameter. See if you can find that one. It's under the function tab. And we'll set the direction on this one to number 1 clockwise. Okay, I think this axis is now also set up. And let's hit save. And we got one axis left. So I hope you're getting more familiar with the configuration now. So let me challenge you to configure axis 5 on your own. Remember we said we would model this as a direct drive rotary table, calling it axis Z with units of degrees. We will use the overtravel on this one because there is that remote demo IO wired to it. But let's set up this encoder also as incremental. And one hint here for you is if it's a rotary table, there is a machine cycle. As this table goes through one complete revolution, it ends up completing one cycle. So why don't you pause the video here and try to do it. And when you're done, I'll show my solution next. Okay, here's my solution for axis Z, the rotary table, on node number 5. First, we'll change the axis name to capital Z, and it's a rotary table, so the load type is rotary, meaning that it is capable of infinite motion in one direction. Therefore, the machine cycle should be set, and one cycle is one rotation of the motor, 360 degrees. So we better change the units to degrees. And the feed constant, the number of units per rotation, is also, in this case, 360 degrees per rotation of that table. We can leave the gear ratio set to 1:1. Under overtravel, we will use the overtravel, so let's leave those set to default. Under function, the direction wasn't really specified by the application, but let's just leave it then at counterclockwise for forward. This is a 100 volt amplifier, so it really doesn't matter for power selection whether you apply 3-phase or single phase. This is really talking about power selection for 200 volt amplifiers. Let's just leave it at 3-phase. It doesn't really apply to this model. And now over here to absolute encoder. We said we would disable that for now and use absolute encoder as incremental. So let's set this here to incremental operation. And that is the basic configuration for the Z-axis rotary table. Let's do a final save. And let's do the reboot this time. Click OK, and under the online menu, choose Reboot Controller. Okay. Now, while this reboot's taking place, let me propose a similar scenario for axis Z. What if axis Z was a rotary placer with a tool every 90 degrees, or it could be every 120 degrees, really depending how many tools there are in that rotation? How might the configuration change? Here on the right, I've got an animation of a rotary placer with a tool every 120 degrees. And also here's an animation showing a 90-degree rotary placer. Well, it could be to your advantage to set the machine cycle to 90 degrees or 120 degrees. This would simplify your programming because you would not have to worry about which particular station is choosing. There would be just a machine cycle, and your positions would go from 0 to 90 or 0 to 120, depending on what you set that cycle as. To bring that here to the hardware configuration, you may, in this case, set your machine cycle then to 90 for a 4-station rotary placer, or 120 for that 3-station rotary placer. We will not set up our machine for that. That was just a little extra credit to think about. So be sure that machine cycle there stays at 360. And your final step with this configuration will just be to confirm that it works by doing a test move. And that's the next video in the playlist here. And that video is created on a different demo, but the test move still operates the same. So take a look at that video and run a test move. Just connect to the controller again. And the test move just amounts to going online in the test move tab and putting in some appropriate distances and speeds and accelerations. Turn on the servo and click start. And if it moves the right distance and you don't get any alarms, then that axis is good. Thank you for watching this video, and remember yaskawa.com/IEC for more information on the MPiec product line.